Look up at the night sky, and the moon feels like a standard fixture, a quiet, glowing rock floating overhead. But from a planetary science perspective, its presence is a profound departure from the norm. The inner solar system is practically empty of natural satellites. Mercury and Venus have none. Mars only has two tiny, potato-shaped asteroids that it captured. Then there's Earth. Our moon has a mass ratio of roughly 1% of its host planet. In the context of rocky inner planets, that scale is unparalleled, defying standard planetary formation models. This mass creates a complex orbital dance, where both bodies revolve around a shared center of mass, called a barycenter. That pivot point is located about 1,700 kilometers deep beneath your feet. A companion this massive is too large to be a captured asteroid. Its existence and its composition of silicates nearly identical to Earth's mantle suggests a singular, violent genesis event. We have to rewind 4.5 billion years to the early Hadean eon. The solar system had only existed for a few dozen million years. A Mars-sized protoplanet named Theia had been growing in a nearby orbit. Gravitational pulls from other young planets eventually destabilized its path, sending Theia on a direct, high-energy collision course with the proto-Earth. The impact delivered enough energy to melt both bodies and vaporize a massive chunk of Earth's outer layers into an explosive ream of silicate debris. We know this happened because the evidence is still buried inside our planet. In late 2023, researchers using advanced seismic tomography identified two massive, continent-sized structures near the Earth's core mantle boundary. These are known as large low-velocity provinces. When the collision happened, Earth's lower mantle wasn't entirely molten. The heavier, iron-rich core of Theia survived the impact and sank deep into the Earth, forming those dense anomalies. Meanwhile, the lighter, vaporized rock blown out into space coalesced in a matter of decades. This sequence of events explains why the moon has such an unusually small iron core and a massive rocky mantle. It is a permanent, physical scar from Earth's near destruction. Right after its violent birth, the moon spun rapidly, but it was much closer to Earth back then and still partially molten. Earth's intense gravity stretched the moon's crust, creating huge tidal bulges in its surface. As the moon rotated, these bulges sifted, generating internal friction that bled away its rotational energy. This process, known as tidal braking, continued until the moon's rotation slowed down perfectly to match its orbital period. Today, it takes precisely 27.3 days to spin once on its axis, and 27.3 days to circle the Earth. This state is called synchronous tidal locking, and it explains why one hemisphere remains permanently hidden from our view. But gravity works both ways. The moon pulls right back on Earth's oceans. The side facing the moon gets pulled the hardest, creating a vast bulge of water. On the far side, the gravitational pull is weakest, and the simple inertia of the water keeps it moving in a straight line, creating a second opposing bulge. As Earth rotates through these stationary bulges every day, we get our tides. This constant movement of water acts as a global circulatory system. It drags heat from the baking equatorial regions up to the frigid poles and prevents coastline waters from becoming stagnant by constantly churning oxygen into the seas. The moon also regulates our seasons. In 1993, astronomer Jacques Lescar ran simulations proving that the moon acts as a massive gravitational anchor. It tethers the Earth, locking our axial tilt at a steady 23.5 degrees. Take the moon away, and the gravitational pull from other planets, primarily Jupiter, takes over. Earth's axis would swing wildly in chaotic wobbles, tilting anywhere from 0 to 85 degrees. The poles would alternately point directly at the sun to boil and then swing out into deep space to flash freeze. By locking in our tilt, the moon operates as the ultimate climate regulator. It provided the billions of years of uninterrupted environmental stability required for complex life to evolve and adapt. While the moon stabilizes the climate for life, it may have also provided the mechanical catalyst to kickstart it. Billions of years ago, when the moon was significantly closer, its gravitational pull was immense. The oceans experienced violent tidal surges that flooded the primordial coastlines every 6 to 7 hours. This relentless rhythm is the basis of the tidal chain reaction theory. During the extreme low tide, shallow pools dried up, concentrating raw chemical precursors so they could bond into complex chains. Then, hours later, the violent high tide rushed back in. diluting the pools and causing those double-stranded nucleic acids to pull apart into single strands, ready to replicate again. These massive waves also acted like a centrifuge, sweeping heavy radioactive elements like uranium into concentrated deposits at the high water lines. The radiation from these beaches provided a constant, intense energy source that could synthesize the very first amino acids. In this hypothesis, the moon acts as a mechanical pump, physically driving the assembly of life's first chemical building blocks through these rapid, high-energy cycles. This 4.5 billion-year history is a forensic timeline built from the only celestial body humans have ever physically sampled. For a long time, scientists thought the moon was a cold, inactive rock, but between 1969 and 1972, Apollo astronauts brought back 382 kilograms of surface material. Inside trays of lunar samples like these, geologists found anorthosite and basalt, rocks that formed directly from cooling magma. It was hard proof that the moon was once a globally molten ocean. Today, we are transitioning from the brief scientific sorties of the Apollo era to the permanent infrastructure of the Artemis campaign. Artemis will target the lunar South Pole, a region defined by towering peaks bathed in constant sunlight and deep craters locked in eternal darkness. Inside those dark craters lies ancient, trapped water ice. By mining that ice and splitting it into hydrogen and oxygen, we can manufacture rocket fuel and breathable air right on the surface, turning the moon into a vital refueling station for the journey to Mars. This binary partnership is not permanent. The Earth-Moon system is a transient phase in the life of our solar system. Because Earth rotates faster than the moon orbits, the tidal bulges in our oceans are constantly dragged slightly ahead of the moon's position. The gravity of those massive waves pulls forward on the moon, stealing rotational energy from Earth and transferring it into the moon's orbital momentum. You can measure the result. Earth's rotation is slowing down, meaning our days are gradually getting longer. And as the moon absorbs that stolen energy, its orbit expands, pushing it away from us at a rate of 3.8 centimeters every year. In roughly 600 million years, it will have drifted so far out that its apparent size will shrink in our sky. It will no longer be able to block the sun's disk, and total solar eclipses will end forever. Eventually, the two bodies would reach a state of mutual tidal locking, where one side of Earth permanently faces the moon, and a single day stretches to 47 of our current days. But they will never reach that perfect balance. The expanding red giant phase of our dying sun will engulf them both long before that happens. The moon was born from a violent cosmic accident, and it is slowly drifting into the dark. But for this brief, miraculous window in geological time, it serves as the indispensable engine that makes Earth a living world.